We're now going to look at how to more systematically derive the different orderings of the loop when computing a matrix-matrix multiplication. Remember that the ij element of C is updated with a dot product of the ith row of A and the jth column of B. Now let's illustrate this. There are three loops. The j index keeps track of the columns of C and B with which we are computing. The I index keeps track of the rows of C and A with which we are computing. If we replace the summation that was the dot product, then we end up with a loop indexed by P that adds the dot product to the ij entry of C. Let's illustrate this. We start by pointing j to the first column of C and I to the first element in that column. We then need to do a dot product of the first row of A and the first column of B. Then we update our index I, we look at the second element in the first column of C, and we do a dot product to update that element. And so forth, until we reach the end of the first column, at which point we update our index j, and we repeat the same thing for the second column of C. We already have written routines for implementing a dot product, so why not use it? If we again go back and we start looking at how to compute the first element in the first column of C, then we can simply think of that as one dot product, which means we replace the innermost loop with the dot product that implements it. We could do that by, for example, calling the dot routine that you wrote earlier in the course. For each of the elements in the first column, we perform a dot product to update that element, and then we move on to the next column and do the same thing. And if there were more columns of C, we would simply keep repeating this process. We can also recognize that we were computing the matrix-matrix multiply, updating C one column at a time. Now we learned that each column of C is updated by A times the corresponding column of B added to C. So we could simply replace the inner two loops with the matrix vector multiply that they implement and have one loop indexed by j. In that case, we treat A as a matrix, the jth column of B as a vector, and the jth column of C as a vector, and we do a matrix vector multiply, adding the result of that matrix vector multiply to the column of C. Now, more formally, we could arrive at that same algorithm by starting with C being updated by A times B. If we partition the matrices C and B by columns, then we recognize that the jth column of C is updated by A times the corresponding column of B added to that column of C. So this summarizes the computations that need to be performed with the different columns. C therefore can be updated one column at a time. So we get a loop indexed by j, where for each j we update the jth column of C with the product of A times the jth column of B added to that column of C. But that matrix vector multiply itself can be implemented with two loops. If we order the loops that implement the matrix vector multiply as shown, what we are really doing is computing the matrix vector multiply with dot products. Alternatively, we could use XPs, and that is simply a matter of exchanging the two loops that implement the matrix vector multiply. So, a matrix-matrix multiply can be implemented as matrix vector multiplies that update the columns of C one column at a time.